Okay, hi Matthias. I will wait another 1 or 2 minutes. Probably a few more people will join in. If you have any questions about data curation or anything else, yeah, just ask. Yeah, otherwise we just wait a few minutes.
Well, actually, I have a problem with the upload of the data.
Okay.
I'm not sure. Maybe we can speak after the lecture.
Yeah, but the idea is also to have a bit of today, like address issues which happen with the data upload. So I think it's pretty good to have like just show some general problems which appeared or general questions, and yeah, so I think we will just go through such points. Okay, give me a second. I have to share my screen, and then we basically go through the yeah, we would go through the studies first and see what is going on in the data curation, see where the problems lie, and then we would work on the full body model for ramipril and ramiprilat. Okay, 1 second. I just have to share my screen somehow. So share. Okay. Okay. So let's start with the data curation. I will just pull the latest changes, and yeah. So, and I will show a bit exemplary how would I debug things and figure out what is going on. So first thing I have to figure out, okay, which study you're working on. I think you're Mati 1 or something, or yeah.
Yes, I'm on Noiri. Yes.
Okay, perfect. Okay, looks nice. So you want Shioniri. Okay, so quickly have to open the data. Normally, what I'm doing when I look at the stuff is okay. So other data, XResearch data studies, ramipril. Okay, first I will just look in the folder and see what's going on. First thing, yeah, let's write all the extensions small. This is the figure. Yeah, looks pretty good. And yeah, here I think the only issue is a bit the quality is bad, but the points can still be detected. There definitely will be some issues here with this axis. If you recognize that, like they have different distances here between the these data points. This definitely will be an issue here. Otherwise, you always have to check if there are log axes and so on. No, units are okay, and you have 2 groups, and so the thing is like to figure out the groups.
That would actually be my first question, because in the PDF file they talk about 11 patients, and one group is 6 and the other group is 5, but then in the figure it's just 5 and 5.
I'm pretty sure they dropped 1 person out. This is often like that. So they were, and this is also a bit problematic. So often the patient characteristics are reported for 6 people, and it's like, well, the patient characteristics are reported for more people, but 1 dropped out, and then the data is reported for less people. So it's more like, like, okay, this mean body weight is for 6 people, but only 5 of them were measured. So the trick how you do this is that you add a subgroup and basically say, okay, I have this group of IRF, which is defined as 6 people with a patient characteristic. And then you add a subgroup which says, okay, this is just the IRF measured or something like that. And there you say, okay, there are only 5 subjects in there, and this is a subgroup of the IRF. But this, okay, we can have a quick look how this looks right now in the table, and then we would check how it is. I'm just looking if there's some patient characteristica. Yeah, probably I'm not sure if they reported for the ideal cases, if they reported for the different the patient characteristic for the different subgroups, but I'm not sure they reported anything here. Okay, so let's have a quick look at the study, how it looks, and just Making this a bit bigger.
I think I haven't done this yet, or at least that's an old version. I think I did some in between, but I didn't upload it apparently.
Okay, so I won't change anything here. So okay, yeah, if you can, just upload it now. Otherwise, yeah, I will just walk through the other studies and do this at the end. So if you can manage to upload that in the next few minutes, would be great. If not, no worries. Okay, Allegrini, we don't have anything here also. So most of these studies, we don't have anything. Gherkins, there was some work on it. Okay, I will just, so one thing would be to check if the study uploads. There's also like just looking if the files look okay. And also to check that, what are the errors really in the upload. So just activating this environment and setting the environment variables here once, and then I can try to upload the study. This is in data, studies, ramipril, Gherkins. Okay, let's see what happens. So here study JSON is missing, and then we see here also, okay, this is clearly there is a JSON in here, but the naming is wrong. So this JSON file should always be called study JSON. That's it. And we can have a quick look in the study JSON how it looks. From there, yeah. Okay, definitely these mappings don't look correct. Okay, so we will solve this in a second. So let's look at the figures. Okay. Okay, this screenshot I don't like so much. Okay, first thing we can see, okay, we again have this issue with this axis. So these are definitely there's a different axis units here, but this looks really like really stretched the image. So I want to check if this is looking like that in the original publication. Because the problem is if the image is stretched, then also the data curation won't be too good. No, here looks I don't know, this looks much cleaner. So I will just update the screenshot first. Yeah. So the problem is there can like it's never good if the image doesn't look good. There can be it looks like this was stretched or the resolution was really low. So let's just export that and get XResearch data studies ramipril, and I'm in Gherkins. Okay, Gherkins, and this was a figure 1. Export, replace. Okay, export, and most likely the other screenshot will also be affected. So I will just create this right now. Edit. Paste as. Tool. Okay, nice. So the screenshots should be better. So let's have a look at the Excel file. Okay. Okay, there are definitely some issues. Okay, let's start with mostly I look first at the data and just to figure out what is going on. But there are definitely some issues. Let's see, but probably nothing too bad. It's always to figure out what is going on with the first thing is to figure out what is going on with the study and if the right things were measured. So for instance, here we have mean plasma levels of ramipril and ramiprilat after oral administration of 5 mg ramipril. So a quick check if this is okay. 5 milligrams. This looks good. Single dose oral. This looks all very nice. I would give this just an ID, real PO, and then we can use this here. Okay. Things which are definitely missing are the okay, study ID looks good. Intervention, yeah, it's probably one group. Okay, this looks also good. This is the all group. Quickly checking if the group, yeah, this looks nice. At least the group name is correct. So the count, I have to check that, but probably 27. It's more like I would write it in here, but for me, it's often what I'm doing if I'm unsure about things, I will just make them yellow. This is for me more like, okay, this okay, at some point you this has to be really checked if this is correct. I think it's also good, like on or writing comments behind here. Okay. The other thing is we we need the interventions. These are not here yet, so in this case, it's we define the ID for the intervention and would say, okay, in this case, we gave the 5 milligrams. And then here, it looks like the times are here, but the values were put in the measurement type. So this is basically the wrong column. We're pretty sure this is mean data because it's from a group. So we put it in the mean column. And this looks just like, okay, this was put in here, and then we don't need this. The measurement type was really a concentration, but for every data point, we have to define that it was a concentration. We put this through here. Here, normally all substances are written through lowercase. Moment. Normally this, why is this auto? Ramipril. I hope this is not, why is it changing? So, okay, no. This is also like with this autocomplete, it's never good. So this is ramipril, it has to be lowercase, and then we have ramiprilat, it also has to be lowercase. So this is the lower part. And yeah, so you can see there's lots of things going on. I would use the same labels here for now. These are time courses, ramiprilat, and then I would remove the rows we don't need. There's no information here. Okay, and here there's also no information. Okay, delete row. Let's see, we don't have any errors. The units look good, nanomole, nanogram per milliliter. So normally I also give this freeze first row, freeze first column. This makes it often easier to navigate. And the only one thing is here that the tissue has always to be checked. So these are plasma levels. So they are not measured in the urine, but they are measured in the plasma. Okay.
I was actually pretty confused about this because, like in the article, they mentioned that they count the ramipril and ramiprilat level in urine. So I was thinking maybe I should write urine there.
No worries. No. Here it's really about, okay, we try to understand what the data was, which was in the figure. So they definitely used, okay, so they probably measured also urine, but they didn't report the urinary time courses. But if you read something like that, it can be very likely that that they reported pharmacokinetic parameters for that, like for instance, recovery in the urine or something similar. So you have to look out for such information. So there's somewhere systolic blood pressure here. So they let's quickly check. Yeah, and it's metabolized in the urine and plasma. Genau. Yeah, so they definitely measured it in the urine, but they probably didn't report it at all. So you have to be really read it in detail. If there's somewhere some urinary recovery value, because this is really strange. Why would you even mention that you measured in urine if you don't provide a single data point where you showed something in urine? Sometimes it's also like here, like it looks like they reported it here. Here, you'll see this is the important sentence here. It's, or I can't mark this, but okay, the total recovery of ramipril and metabolites in urine was on average 39 plus minus within 96 hours. So this is basically a pharmacokinetic parameter which says, okay, the urinary recovery of ramipril plus ramiprilat was around 40%. So this is like this would be a parameter which we have to write in a table, like basically create a table for that. But this is I would say this is all the information you get here from the urine. It's just a single value, but it's an important value. And it says like after 96 hours we got 40% in the urine. Yeah, but for this curve normally it's this is plasma or serum if you have ramipril or ramiprilat concentrations. And also in the urine, the curves look different. If it goes up and down, it's plasma or serum. If it's just going up and up, then it's normally urinary recovery or amount in the urine and so on. Because it's basically it's never going down because you're not removing anything from the urine. It's just going there. Okay. But this is a good point. But this is always like this tissue basically means, okay, for this data set which you did, this is a tissue. Okay, last thing I would check here is the data points, and I'm pretty sure you overlook this here because you can see the last data point is at 240, which looks pretty good, but the point before is at 210, and this is definitely not 210, but this is 24 hours here. So it's okay. So okay, so you messed up a bit, but okay, but this is like an error which is pretty like it happens a lot. So we know basically this is the last time point is definitely 240, but the other time points are wrong here because you used basically you clicked on the wrong point when you calibrated the axis. So okay, unfortunately you have to redo this or figure out what the time points were from the paper. Sometimes if you're lucky, they give really the actual time points in the publication. Let's see, where's the PDF here? So if you're lucky, they reported somewhere we measured plasma concentrations at time points so and so and so, but in this paper not. So you really have to figure out what the time points were, and in this case, yeah, you have to redigitize this figure, but it's not much. It's like 20 points. But you have to be careful, like if you do the calibration, that you on the x-axis click on the 0 and on the 24, and here on the 0 and the 50. You also see here's a little offset, so you have to use different values for the 0.
Yeah, that was actually the problem because I was digitizing plot like 3 times.
I know. Okay, this is, but this is also like, okay, this is shows how difficult it is. The point is you really have to say, okay, I want a different y value for the digitization of the y-axis, because you have to click, basically you have to click 4 reference points, the 0 and the 24 for the x-axis, and the 0 and the 50 for the y-axis. And then you get all this data point, and you will also click on this last data point, and it will say you something like 26 and this value, and then you just replace the 26 here with the 240. Okay, so you have to be a bit creative to get the right data in the plot. Okay, but otherwise, okay, I would say this is this looks good. It's just like this is this happens pretty easy. It's similar things with logarithmic axis, that you just digitize it in normal instead of logarithmic and so on. But here this is not an issue. Okay, this looks good. Otherwise, I would say here it's I'm not sure what you did here. Okay, but okay, I know approximately what you did here, but the ideal thing is that you just copy the table how it is. Then you know which fields should be there, and then you have the right table headings, and then you try to fill everything out. Okay, let's have a quick look at the. Oh, I have it open already. Okay, but these are all like typical things which happen, and especially because if you do this the first time, it's pretty unclear what to do. So you have the best thing is just to do something, and then I can give feedback on okay, what it is. And most of the time, it's in 5 minutes. Things can be fixed, and this is pretty good. Yeah, here. Yeah, you also have the offsets. Here the times are better. This is like the nice axis. So this time points look say this look pretty good. Just with the values, I'm really confused. Basically, I would expect I get a value around 100, and then it goes down. So I would expect like for the first time points, I get something around 100 here. But there's some 3 in here. In the end, it goes up to then 79. This looks good, but it could
Actually,
be that
I started to
started down
click
here.
click the points, yeah, from the down point.
Exactly. But this is a curve where you don't have the points. Like you should just basically just click at some points here on the curves. Like basically do this. This doesn't have to be perfect. It's just but this downgoing flank is really important at the beginning. And then the rest looks good, but it's probably like 2
Okay,
more
then
points
I'll
here.
add more points.
Exactly. Yeah, it's more like in the end you have to always imagine if we plot this against each other, then it should look like this curve. That's the main thing what we want to get out of here. Yeah, but otherwise this looks good. Percent you always have to write as percent. Yeah, patients with a heart failure, this should be encoded via the group. So it's basically you yeah, you have the, let's say you have the group information. The group is all, and on the group you should have yeah, it's basically patients with heart failure. Okay, here one thing you have to split this in the information. Here's probably the mean value plus minus SD. So you should write the mean value in the mean column and the SD value in the SD column. So you have to basically split this information and write it in 2 different columns. Otherwise this looks good, but it's more that you say here this was the all group. It's already encoded that this is that these are the people with a heart condition, and yeah, please use the same headers here, and then you will have also the all group, and then it's clear that these are patients with heart failure, and we don't need this information in addition here in the table. Okay, looks good. Okay, otherwise, yeah. But this is the right thing. Unfortunately, you have to redo a bit of the digitalization. Probably you don't need individuals because you only have mean data reported. So you only need the group. Okay. So yeah, I would suggest you try to fix the issues here with the figures, and then just get into contact, and then I can help you with a study JSON and to make this upload.
Okay.
Perfect. Okay, just saving this. Yeah, but this is really nice. I'm happy with that. Because it's infinite times better than having nothing. So you have to say like that's a point. Like if and it's often it's easy to fix things if they are a bit wrong, and so okay. Okay, so the let's see what's going on. What did I put? Okay, so we have the updated Shinuri. Let's have a look at that. That's from Mattis. I just have to reload probably. Okay, perfect. So yeah, I will just try to upload this to see what's going on. Yes. Okay, the good thing is a lot is already happening. There's some complaint about the units of the blood pressure. This is blood pressure categorical, so we have this is most likely something in the group. Yeah, and basically, it makes somehow sense that, like, if you say something is elevated, it doesn't have a unit. So so let's upload this again. Now is 11 patients, subgroups. Okay, that's okay. This is other. Okay. Here we probably need some. There are a bit of additional fields. Which could be used. I will just go in the Curation. I think that this is it looks like a function with renal, like a study with renal impairment. So there's definitely if there is something about the renal disease reported, but there is also let's see, there's also like some renal disease where we have mild or moderate. Sometimes they report this. Okay, we had a group which was normal and the other were mild or moderate renal disease. I think there's also something like kidney function. Like creatinine you did, or like if they report a glomerular filtration rate, this could also be this is something to encode. Yeah, but yeah, definitely there should be some field on the group which says, okay, the one is renal impaired and the other not. So this so I definitely would put more information here, but it's you have to look if you find something which could fit here and describe these groups better, that we know the one is healthy and the other not. So you can definitely like oh man, I have no clue which is the healthy one.
I think you missed some columns on the left.
Okay, perfect. Top. Yeah, here. Normal renal, exactly, impaired renal function. So this is the normal one. Yeah, so definitely for the normal one, I would yeah, like here, this is basically, you wouldn't write healthy no for all of them. This doesn't make much sense, but you would more write this on the individual groups. So you would have basically you would say the these 5 were healthy, and the other 5 were not healthy.
I think the problem is that all of them were hypertensive, so that's why I thought they were all like not healthy.
Exactly. Yeah, okay. Now you're getting in this gray area. Like I have no clue. When is a person not healthy anymore? This is more like, okay. For me, it's like a bit blood pressure is okay, but I would say this is probably the oh man, it's difficult. Okay, I get your point. Okay, I get your point. Oh man, this is, yeah, but this makes it always difficult to compare things. I can already see, okay, so let's leave it like we had it. This is good. Healthy 11, no, but we should definitely, yeah, all were blood pressure elevated. This is written down, really nice. Okay. Okay, I like that. Okay, that looks good. Individuals we probably don't need. Ramipril, this looks good. Trial 5, okay, this is also something nice. Tab 1, and then you did the figure 1. Okay, so I'm pretty sure we
I still have to do the digitalization, but yeah.
For the tab 1 or what? Or
yeah, I didn't do it yet.
yeah, no, it's okay. But here the yeah. Okay, now I get it. The numbers are missing. Okay. but yeah, but this is exactly now you would basically in the end you would digitize 4 curves with the mean and the SD, and then basically it would just change here the group and the substance, and then you have to give different labels for the different subsets, and that's basically it. I think you can look in the Witte, there's an example for that, or the other studies. But yeah, but otherwise, this looks really nice. I like this. Units are also good. Hours. Okay. Yeah, perfect. We'll have a quick look at the other table. Okay.
Yeah, I wanted to make the table out of the text because it's just in text format.
Mm-hmm. Makes sense. Makes sense. Okay, then just call it something. Call it tab A or something like this. So user numbers are normally the numbers are for there's an actual table which exists for that. Otherwise, I give just tab and something else, and then it's clear. Okay, this is somewhere from the text, and write in the comment like, okay, this is from the text. Okay. Yeah, very nice. And then yeah, then the remaining arrows are probably let's see. I have to check. There's still something in the characteristica. There's something there for clearance. It's not allowed. So for clearance, you normally need a unit. So somewhere you have in the in this table some incorrect unit. So let's have a quick check now. Somewhere you wrote clearance, and this is here. And you see basically here you wrote the unit, and the unit was just in the wrong row before. That's why. Okay, so makes sense. And okay, and then it looks good. Loads up. You probably didn't map the figure yet. As soon as you now would probably be also a good idea to start mapping the figures, and then you get already feedback. Okay, what is missing and so on, and it will complain that there's no data in here and so on and so on. Okay, but very happy with that. Just closing everything here. Close our tabs. Okay. Exactly, Witte, I finished, and so I don't know, Schunkort uploaded, I think last time. Meyer, we have the figures, but no Excel yet. Oh, much is a lot. So Lou, let's check if there's uploads. Okay, but looks good. Data is coming in, and yeah, here study IDs are not correct. This is often like you just have to check that in all your tables. The first one is yeah, this is also a typical error that you just take that and pull it down, and then Excel also is just putting everywhere this wrong IDs. So just yeah, also it also shows like how easy it is that Excel is just destroying your information. This is like it looks. Here you can see this looks strange. Like okay, well, this is only like you have to be a perfectionist with this stuff. Like here you can see like one of these has a little bit of offset. So there's definitely a white space somewhere in this in one of these, probably in the last one. Yeah, you can see here's a white space. So this is also not good. But this is like errors you okay. That's why I always like try to align the stuff in the middle. Then you see this white space issues easier. Okay, otherwise this looks nice. Top interventions looks good. Figure 4. I don't like that I don't see data and SDs. So definitely, it's never good if you have like you have here the time points, but you don't have the data. This is like something definitely went wrong here. And you also have to figure out what is this? Is it SD or SE? This error bars are pretty large, so I would say this most likely SD. But this you have to figure out, and where do you put it? So this is just this for me really strange that you have the time points already, but you don't have the data. Serum concentrations looks good. Concentration. This is ramipril because we have a fast decrease in a few hours. So this also makes always sense, like to look, okay, we know the ramipril is going down after a few hours, the ramiprilat after 24 hours. So just make a check if this can make sense what you write, because sometimes the people are just writing the wrong thing at the axis. Nanograms per milliliter hours. Okay, this table looks also really good. Just data is strangely not here. Figure 5. This looks a lot like figure 4. Okay. This should probably look like figure 4. Same thing here. No clue why the data is not here. Well, sometimes as always, it would be interesting. I'm just confused. Okay. But we can see this looks pretty good. And here this top. Okay, we have this first row. We have similar issues here with the IDs. The count of 10 seems to be off. This is definitely 18 here. So no clue why here is 10. What is this? I'm pretty sure this should be 18. Here, similar things with the down pulling. This is all 10 milligrams of ramipril. Okay. Ramipril, ramiprilat, serum, HPLC, mean, SD. Okay. Here I can just say first thing is there are definitely some things missing here. 2, 4. I see 2, 4, 6 rows. Here I see only 4 pharmacokinetic parameters. So definitely parameters missing, and this makes it there's something wrong here, and this makes it also much easier afterwards to read, because you just go through these values and you can check if these are the same values, but somehow the KL is missing. This is the elimination rate. So I think this is KL. And I'm pretty sure only one AUC was done. The AUC inf, but we have also the endpoint AUC. So we have to write also the AUC end. But have to encode the actual time. So here we have to write something until when was the AUC end. And it's pretty clear that this is until the last time point. But basically we need this additional 2 parameters. This is SD, looks good. Okay, perfect. This looks pretty good. Just a bit more data missing. This looks nice. Just saving that. Let's see. There's probably some issues still with oh yeah, here we have yeah, because there's the empty fields. It's okay. And let's have a look at the study JSON. Okay, this is nice. XResearch is in here. Exactly. For the names, use your GitHub IDs. You can now I added the remaining users, so please add also yourself to the curators. So you can write the XResearch this here, and I will also go over that. So probably it's always 2 in the XResearch, which should be here in the study JSON. Okay, also very nice. Yeah, much so much stuff for. That's what I mean, like you yeah, because you have to do you have to do a lot of figures here. And you have to do a lot of parameters. Table 2 probably not. Let's see what you okay. This I like. This looks all okay. This looks all really good. First look is pretty good. Labels here. I don't like that they end in this lowercase stuff, but this is okay. Not sure. There's probably something wrong with the labels here. Otherwise, this table looks really good. Same here. Here I'm not so sure what happened. This is probably you tried just to fill this out, but here in the first one you see there's only data until, I don't know, around 10 hours or something. So you don't need this this additional empty rows here. This is not providing any information. So I would just in this case I would leave the 8 in here, or like, I don't know, the 6. For me, it looks like there's definitely here a point at 8 somewhere. It's probably in the lower somewhere. Yeah, but this empty rows, it's more like, okay, you can remove that if there's no data in the plot for that. These empty rows are not providing any information. Otherwise, table really nice. Also here, this looks all really good. Okay, but this will take longer to check because there's a lot of data in here. But first view is this is really good. Also that looks nice. Very nice. Okay. Blue, we already checked. Okay, and I think that's Lee. There's also stuff coming in.
I would like to talk about this. That's my paper.
Yeah.
Because I really had some problems getting data out of my visuals.
Yeah. So yeah. Okay. 1 second. So okay, just committing this. Doing this. Okay, let's have a look. Yeah. Okay. Yeah.
Because I tried to get the graphs out of these 4 graphs that are over each other, but even the first time points are set after 15 minutes and 30 minutes, and it's so hard to see. Yeah, so in the end I just gave up and
I know.
Just try to make the first one just into how do I put it? Just get some kind of mean from all these graphs. Yeah, and
yeah, I get your okay. I totally agree. This is here. This is like these nightmare papers where everything is over each other. And okay, the B you definitely can make it. This you can manage. And you have to say also, like, if you miss, like basically if you miss a point here, it's not too bad. You know, you can just, if you're totally unsure, skip it. But if you still have like most of the points, okay, you're pretty good. So I would say the lower part is doable. The upper part here, in the end, I would, if everything is over each other, I would just click in the middle. And in this case, it's more like, okay, I think the key message is here, okay, if we give the stuff an apple juice or water and so on, this doesn't make a big difference. We see basically the same kinetics here. Bit of differences up here, but this is the downgoing flank and so on. It's pretty similar. And I think this is also what, in the end, even if the data isn't perfect for the graph, the data should basically, like, if you plot it, it should lie over this graph. Let's say it like that. And so you can be in the middle, and in the comments you can write, okay, it was very difficult to distinguish the data points, clicked somewhere in the middle. And that's totally fine here. The thing is, if they are very different, then it becomes more difficult. But here, this just click somewhere in the middle here, and I would say you're pretty okay. And if you can see something for some points, then try to take them. That would be my takeaway. So no worries if this, do it as good as possible. The important thing is try to comment about that. Otherwise, okay. And tables, they are okay, but yeah.
And about the second one, I was wondering if it's how important is it that I don't just interchange some? So the first figure. And the second one, they are really interchanging a lot down there, and I'm not really sure I will get the right data points all the time.
Here, I would say the really important thing are these here, you know, like the changes in the maxima, like basically here, that you get the crosses right here, like basically here where you see the curve 1 is the top, the capsule has to be this one, this peak, and the water has to be the next one, and the 2 apple things have to be the lower ones.
Okay.
And the most important thing is change here, basically change in the C max and this stuff. Here the downward flag, okay, this is not so important here. This here really affects the area under the curve, and the C max and the area under the curve are the main things which change here. So here basically, yeah, I get what you mean here. Like this is just
it's really hard to tell anything.
I know.
Another question to that, I have another timestamp at 48 hours, but I can't really get it. I can't really get the measurement there.
This here, yeah, same here. Just click on it, and here it's basically the important thing is where is this value lying at 48 hours.
Yeah,
of course you have to be careful with this axis. It's similar things that suddenly the axis is just different. And so yeah, normally what I'm doing, I'm just doing the calibration 0 to 25, and then I'm clicking this last point, and I get this last point at 28 or I don't know 30 or something like this. And then, but I know the last point was at 48, so I have to manually change the time in the table. And then you only need to do one calibration. And also, like the best thing is to do only one calibration per plot, because if you recalibrate, of course you get an additional error by calibrating. And so, okay, but also like the key message is you don't have to be perfect, because like every of this data point has a measurement error of 10%. So it's like there's already a lot of error in here, and then you click a bit wrong, and then okay, so in the end we're interested in these big differences between the curves. And if this overall curve, like for instance between this study Lee and another study, if they are in agreement, like so basically if we say, hey, here we have a study with a capsule with 10 milligrams and here another one, then the concentration should be identical or like pretty similar. And if this is not the case, these are the big things. I agree, this is difficult. Otherwise, yeah, exactly, put the data in. And the tables, okay. I will look.
I've also been a bit confused because concerning the, where is it there? The fasting, in my paper there was written that people are on a standard fast feed regimens, and I Googled it, but I couldn't find any explanation for that.
No, it's just write it as a comment. Like for me, I try to do the stuff as good as possible. I have to do a recuration. Like basically what I have to do, I have to read all the papers in detail. I just don't have the time to put all this data in the tables, and then I will check such stuff. And so that's why these comments are so important for me. Then I see, okay, there's stuff going on, and I will pay extra attention. And but often it's the information is just not good enough in the publications, or it's not clear enough, and then we also can't write anything down for that.
Yeah.
That's unfortunately that's how it is. But yeah, try like the clear things should be in the table.
Okay.
And everything else which is getting a bit strange should be in comments.
Okay, thanks.
Okay, but yeah, I have to say this looks pretty good, and we're getting there's lots of data coming in. I like that. So definitely one thing would be to clean up the okay, I'm looking at this now, but yeah, we have to get this data clean, because only for the clean data we can then do the simulations. But let's say, like, if the data is in the tables and uploading, then it's pretty ready to do simulations with that. Okay, so let's change gears. This was basically a bit of feedback about the data curation, but you see there are things which apply for most studies. And
Matthias.
Yeah.
By the way, I updated the data for figure 1 in my Excel sheet, but I think it didn't reflect in your system. Maybe because I just did it.
Yeah, you probably
minutes
just did
ago.
it. Yeah.
Yeah.
Okay. So yeah, just okay. You basically saw which changes I did. That's the point also with the Excel files. It's a bit like, it's always dangerous if other people work at the same time at the Excel files. So just keep your local copy of the Excel file and have a look at the one which I pushed, and put the changes that you have only one version where all the changes are in, if this makes sense. Yeah, but no worries. This looked all pretty good. I just missed the data in the one field and the thing. Okay, so let's yeah, but I have to say this works good. And yeah, if everybody's doing in the end 2 studies like in the whole course, then we will be perfect. Then we will have around 20 data sets and so on. And then this is pretty good for such a model. Okay, so next thing is what we did so far in the actual model is that we build the this kidney in the liver model. I will just open Cytoscape so that we can have a quick look. And we basically had 2 files, one to build the kidney model, this kidney model pi, and the liver model, but we don't have a whole body yet to connect these 2. Like, we learned a lot, like in the last few weeks, about ramipril, ramiprilat. Also by looking just at the data, you learn a lot about that, and so we just have to check if what we did in our models is correct and makes some sense. So first thing is I would just look at the kidney model and see what we have in here. For that, it look use the visualization, and what we see, we basically put in the model ramipril, that the kidneys can excrete ramipril and ramiprilat. We check if we already have other information about this. So yeah, excretion. Yeah, so ramiprilat. Yeah, the point is like, yeah, what I see, like, for instance, from here, what I see, okay, ramiprilat is one of the things which is coming out, but it seems like there are a lot of other metabolites which are also coming out. This is basically for the mass balance. This is important, so that we see like a lot of things are coming out, but it's not only ramiprilat, and it's basically no ramipril. This is what I would hear from this study, but it's there's not much. We don't have much data in here. There should, in the studies, there should definitely be more about urinary excretion. But for now, I would definitely say, okay, something else than ramipril, then ramiprilat is excreted. Ramiprilat makes around 50%, or 30%, but we don't need ramipril. So that would be one first update I would definitely make to the model right now. to quickly fix that and basically just adding some changes here. So we would build a version, I don't know, version 2. So okay, this is remove. That's what we will do. Removed ramipril excretion. Not found in urine. And I would also add a bit of notes here. So ramipril is not found in urine. Besides ramiprilat, it's around 40% of those in urine, with other metabolites accounting for around 60%. And just adding this study here, so I remember why I did that. And so like this other metabolites, this will be definitely at some point important, because we also see we only have measurements for ramipril and ramiprilat, but what's going on here? Keyword argument repeated. Okay, so I have to put this up here. No, what did I say? So I lost my. Oh, okay. No, the point is like we definitely have some other metabolites in, but we only have measurements for ramipril and ramiprilat, so we have no clue what's actually happening. But if you look at the urine, we see there are like glucuronides and other things, but we don't have any plasma measurements, so we only know there's something happening, but we have no clue what it is. So probably we will just pool all these additional metabolites in something else and call it ramiprilat metabolites. This makes also this is probably the best solution for now. Excretion of and then we have to quickly check back if this is really the this is definitely like okay, we have a bit of glucuronide from the ramipril, but this is not, it's not too much. We have a lot of ramiprilat glucuronide. We have this DKP acid. And hopefully this are also metabolized from the ramiprilat. We definitely need some additional thing in the model which can account for all this stuff appearing in the urine. Okay. I will just call this ramipril. Ramiprilat metabolites. This is good. So so let's that means I would just call this ramiprilat metabolites instead, and we have the ramiprilat metabolite excretion. So let's just fix IDs for that. Met excretion of ramiprilat metabolites. Okay, so this would be the first thing I would change here, just from the feeling, okay, ramipril is completely converted and we're not finding this in the urine. Here we somewhere have still, but it's in the kinetics. I also have to update this. Of course, the reactions for the excretion are using the rat metabolite and put this in the urine. Everything else looks good. let's see if this is building now. Still some ratmetext here. So ratmetext. So, and then it should work. Looks good. And then basically the main thing we did now is, okay, we have the ramipril metabolites. These can be excreted in the urine, and the ramipril can be excreted. Okay, I like that. And then let's have a quick check what we did in the liver. Okay, so far we said, okay, ramipril can be imported. This can go into the liver, and it can be converted to ramiprilat, and the ramiprilat can be exported again from the liver. That's also pretty happy with that. At the moment, we know ramiprilat metabolites are created, but one could imagine that we have like some additional conversion of the ramiprilat to via glucuronation and so on to ramiprilat glucuronides and other metabolites, and these could also be exported. And this was basically like make up the 100% of things which we find in the urine. But for now, let's just add this. Let's add this additional things. Then we also see how we change the models and adding things to that. So in this case, it's we have version 2. And what we add is basically added conversion and export of ramiprilat metabolites. To do this, we have okay, our compartments and everything is the same, but we have to add this additional metabolites in the model. We have currently only the ril and the ramipril, ramiprilat, and then we add also the ramiprilat metabolites. Ratmet. Oh, okay. Here the annotations. I probably also messed this up. So definitely here we have to update the annotations. Here also. Here, yeah, these annotations are wrong. So we don't have annotations for that yet. So just uncomment that, no annotations here, and the same here. I just screwed this up. So no annotations yet. Ramiprilat metabolites in the plasma, and then we need the ramiprilat metabolites also in the liver. Adding this here, metabolites, liver, and this is we still have to fix the annotations. And have to fix the IDs. Okay, perfect. Quickly checking. I just added the metabolites, but didn't have any connections. Okay, this works. This is a good sign. And then we need the additional transporters and the conversions. Let's first do the transporter, the exporter for the ramipril metabolites in the liver. Okay. Export. Yeah, this takes the metabolites and export it. It's SLV max. for now, I'm setting this to 0. So basically this, there is no, oh no, I have to leave this at 1. That's okay. Yeah, the metabolic reactions I will add in a second, I will set to 0, but basically means that we can't create any ramiprilat metabolites yet. Okay. These are the mats. So where I have a red, I have to do a red mat. Mat. Yeah. And this is now I'm doing this quick and dirty. This is definitely something I will check in detail. For now, it's just making this work. Okay, could be checking if this works. Okay, there's still something wrong. Yeah, here we still have a red somewhere here. So it's here. Mat X. Okay, looks good. But that's why validation is always important. RADMET is not listed in the RADMET X. Okay, because we're not. Because I did use the wrong ID here. Why this validation and checking of the model is so important, that you don't have any wrong kinetics or things in the. Basically, what we did, yeah, we added the ramiprilat metabolites. The only thing which we don't have yet is we need an additional conversion reactions. So somehow the ramiprilat can be go to other metabolites like glucuronation and so on. So we need this connection here still. So we would add this metabolic reaction. And for that, we can just reuse the other metabolic reaction we have already up here. Ramiprilat export, and we would add this in between here. And now just have to place this. So this is basically converting now RAD to the RAD metabolites. This is the ramiprilat conversion, and this is taking the RAD and can convert to the RAD metabolites. And like I said before, I will set this to 0. So basically, this is not happening in the liver right now. We just have it as a reaction already in the model, but it's set to 0. This is all ramiprilat, the RAD, and this is converting RAD irreversible to the RAD metabolites. Okay. Actually. Looks good. Let's check if the model build. Looks good. And now we should have the connection between all the things. And here you can see now, this is basically we have a bit more complex pathway. And so our ramiprilat can either be transported directly, or it could be further converted to additional metabolites, which we know exist because we see some experimental data where we find them in the urine. At the moment, this reaction here is set to 0. So this is basically not happening here, this part, but everything is going as to ramiprilat and then in the plasma. So currently, no ramiprilat metabolites will be created in the model because I just put this, switch this out. Okay, so these are our updated tissue models. Okay, and now we have to create a whole body model. This will be a lot more complicated because there's a lot of moving parts. I think the main thing is you should just get the main idea of what is happening. And so I will just I will adapt an existing model. I just have to think what is the best thing to use. Okay, this looks pretty good. So let's use this model, and I will quickly explain what is all in this model, and first try to make this work. Okay, this will be our ramipril whole body model. So just to a reminder what we want to build. Okay, yeah, here's it's basically we want to build okay, ignore the enterohepatic circulation, but we basically want to connect now the different tissues via the blood circulation. This is what the body model is doing. We built basically this liver model in isolation, where we have the ramipril to ramiprilat and ramiprilat metabolite conversion. And we built the kidney model, where we can excrete in the urine now ramiprilat and ramiprilat metabolites. But these are not circulating, and of course liver and kidney are not connected yet. And also we don't have any way to get ramiprilat into the body. And that's basically because we don't have a body where we could give an intravenous dose or an oral dose. So basically we need these additional things, and like we saw in the data curation, most of the studies are oral doses, so we definitely need like some gastrointestinal or intestine which can absorb the drug. That's what most of the tablets, like they are dissolving in the stomach and in the intestine, and then the drug is absorbed in the intestine. So somehow we need this absorption processes in the intestine, and we need this distribution via the blood circulation. Okay, and so now we will build the blood circulation here and connect the liver and the kidney model. Okay, so for that we'll definitely need some templates. Do we have templates here? Yeah, we have templates. So we will use our templates, which we already defined. So this is in XResearch, ramipril, we have ramipril, and here it should be. Import the templates. Why are there no templates? Directory as the sources root, and okay, what else? We want the annotations. Okay, this is strange. Why this is not working? Very strange, because we did this imports before. We did this in models, and there the imports worked. Okay, for X. This is not in ramipril. No. Oh, sorry, I used the wrong. Oh, this was not very clever. I just used the wrong folder structure here. Yeah, we defined this on the top level, the templates and the annotations. Okay. So what do we need for the whole body model? Okay, again, we need much more units, and this is just units for certain things like blood flows, cardiac output, tissue distribution, and so on. So okay, all not so important, but we need a lot of units because all our things needs units. Okay, then similar to the tissue models, we have to first define the model object. I quickly have to check if we that we use the right naming or the same naming conventions like our tissue models. This looks good. Ramipril liver. So we call this ramipril body, and this is our ramipril body model. Okay, happy with that. And then we have to say certain things, like basically we have to say what can circulate in the body. So it depends. We have to say, okay, certain things have to be transported here in the system. And we are only interested in things which are important for our model. In the moment, we only have ramipril and ramiprilat and the ramiprilat metabolites. So these are the only things we could circulate right now, or make sense, because we don't have any other mathematics or kinetics or things in the model. So we only have these substances, so it makes sense to circulate that. But later on, if we go towards the pharmacodynamics and the blood pressure, of course, other things could be important in the blood, like renin or angiotensin and so on. But for now, like we basically have a general definition what can circulate in the blood and what is transported and how is it transported. And this is now what we define here in the beginning. We basically just say, okay, which substances are transported in the body. And in our case, it's ramipril. We're setting at the beginning, basically, we don't have any ramipril. We need a molecular weight for that. I exclude, currently I just say we have an IV dose, and I set a certain rate, but we also don't, okay, at the beginning we don't need that. So we basically just say we can give the ramipril intravenously. And we do the same thing for the ramiprilat. Okay, this we still have to fix. Yeah, ramiprilat is not given intravenously, so basically we don't care about all this stuff here at the moment. And we also add the ramiprilat metabolites as circulating metabolites. This is our RADMet. Also the molecular weights are off, but this is in the moment not important for the model. In addition, we have to define, okay, what do we want in our model? We definitely need the kidneys for the urinary excretion. We need a liver for the metabolism. We need the lung. This is mainly important for the transport of the blood. So the lung is basically pumping all the blood back and bringing oxygen in the blood and creating arterial blood out of the venous blood. We need a gut for the absorption. The rest compartment is basically everything which we don't model in detail. Bones, fat tissue, brain, I don't know. Like basically, if the brain becomes important, then for ramipril, then we could add it here. But this basically we just do the minimal amount of organs which are important now for this for our question. We have arterial blood, venous blood, and these are basically just intermediate points here before the liver and so on, where we can do measurements and so on. Okay, we have certain submodels. In our case, we don't have an intestine submodel yet, but we have a kidney and the liver, and sorry, and this is the name of our submodels. This is basically the ramipril kidney and the ramipril liver we already defined. Gut model we don't have. And then we have to say, okay, where are these models defined? We defined this basically in external files because we created them separately. And now we couple them to the blood circulation here. Okay, like I mentioned, you don't have to understand all of that. It's more like you should get the general gist. Okay, but what are we doing? We're creating the body and trying to connect the things. And for that, you have to define what should be in the body and which submodels you're interested in. So we have certain compartments. This is similar to the tissue, liver model and so on. We have a plasma compartment and a real compartment. Here we have Now compartments for the whole organs, for the gut, for the kidney, liver, lung, venous, arterial. Basically, these are tissue compartments of feces, stomach, and so on. This is just how the body is built. And then we have can basically say, like, if you have an organ, it's consisting always of plasma and of actual tissue. And so you have to create these two different compartments, and in the plasma things are transported via the blood circulation, and the tissues is where the cells are normally of an organ, and where metabolism and other things can happen. And so this is basically just saying, okay, we creating the different tissue compartments. This stuff we don't need at all. Yeah, we don't need duodenum. And then you define certain replacements between volumes. And this is basically just saying, okay, the kidney, which we define separately, we just want to connect it here to the body, similar with the urine compartment, and the liver. We want to connect. We don't have a duodenum. We don't have an intestine. Exactly, we don't have an intestine. We don't have feces and all this stuff. Okay, this we don't have to replace. Yeah, so we don't have feces yet. We don't have a duodenum. We don't have a stomach really. So like we can just remove all this stuff. And here I will just uncomment this, because probably later on we will need it. Okay, and then we our things can be transported via the blood. This is basically what this is doing. It's just creating species in all our blood compartments. And if the things can go into the tissues, it's also creating tissue compartments. Certain things can go in the urine, so we're adding this basically here. In our case, we only the rat and the rat metabolites can go in the urine, and in the feces, yeah, we don't have anything. We don't have an intestine. We don't have any feces in our model, and then we say, okay, what should be replaced between the body and our different models. So for the liver, we definitely have to say our ramipril, which is circulating, should be connected to the liver, our ramiprilat and our ramiprilat metabolites. For the kidneys, only the ramiprilat and the ramiprilat metabolites are important. And for the gut, nothing. Ignore this is in the urine. We have to just define what can go in the urine. This is rat and the rat metabolite. Feces we don't have. We don't have an intestine, so we can just ignore that for now. And then yeah, we have basically the whole body. Quickly have to check that I didn't screw anything up until here. Okay, this is what we don't need. So okay, units, general model definition. We have ramiprilat, the ramipril, ramiprilat metabolites in our models. Tissues look good. Submodels look good. Compartments look all good. Here looks good. Kidney replacement. Just have to check that. Okay, this looks all good. This is just the volume replacements. Then we have the putting the species in the blood compartments, distributing it everywhere. Can go in the urine. Can go in the liver and the kidney. Can go in the urine. Okay. And then we have parameters. There's a lot of parameters which correspond to the whole body. So what we're building right now is a person which is 75 kilograms and 170 centimeters high. Probably a a male person right now, but okay, this is just it's basically a reference person, I would say. So 75 kilograms, has a heart rate of 70, resting heart rate of 70. The body surface area can be calculated via formulas. We have a cardiac output of this. We have like hematocrit of certain values. And then we have to say, how is our body composed? So in our case, we these are basically just giving the fractional volumes. So we're saying here basically 0.4% of our body are kidneys, around 2% of the body are liver, around 0.7 or 0.8% of the body are lungs, and so on. So these are just standard values, how big things are. Most of the stuff is really normally muscles and adipose tissue and bones, and the important organ, or like the important organs, they are not so big, so they're normally in the few percent ranges. In addition, we have fractional blood flow. So how much blood flow is going to the different tissues? This is mainly what we see here. So you see like the lung is like pumping 100% in the one direction, and then around 20% of the blood flow going through the kidneys, around 15%, around 20%, like 5 plus 15, go through the liver, and the rest is basically 60%. So we have different tissues. Some are fast perfused, and other low perfused. And this parameters just define, okay, how much blood flow of the total blood flow are the different organs and the whole body getting. And okay, there are other things. Okay, these are not important, these parameters. This is not important. Okay, and then basically we're not replacing any parameters. This is molecular weights. We don't have F tissues. And then we're adding some equations that we can basically do some intravenous dosing. This is what is happening here. This is okay. We don't need this here. We need a cumulative dose of the infusion to calculate certain things, a rate of infusion, how fast do we infuse, and so on. And in the end, we basically build the whole body. Like, for instance, this rest compartment is the total body minus the other fractional volumes we have for the organs. And similar things we calculate for the blood flows. There are basically flow conservative, basically like what is flowing in an organ must be flow out of an organ. And also the sum must correct. Like if 100% is flowing in the one direction, 100% has to flow in the other direction. So it's certain things have to be conserved in the model. And by calculating these via equations, we are sure that in the model these things are conserved. For instance, and then the actual organ volumes are calculated as a body weight times the fractional organ volume. So if our liver mixed up 2% and we weigh 75 kilograms, then our liver is 1.5 kilograms. If this makes sense. So and then basically if we have a person who is 50 kilograms, then we know the liver is 1 kilogram. Okay. And that's basically why this is important, because we can basically scale our model via the body weight and the height and build like different people. And a lot of these things automatically scaled. And this is what is in all this equation is happening. It's just calculating the things based on this basic parameters in the model, body weight, cardiac output, and so on. Calculating blood flows. Using, of course, hematocrit and stuff like that to do these calculations. Okay, and then certain things. Okay, a lot more stuff is calculated, but most of the stuff you don't have to be aware of. Red met, feces metabolites we don't have, so we can ignore that for now. And then we have a lot of transport reactions. Okay, this is transport if the substances can go in the tissues. We don't have this. We have the dosing equations, and then we have transport flows between the organs. This is basically now what the equations which are defined here. They are they are basically the transport equations here. So substances which are in this compartment in arterial blood can be transported via the this blood flow in the next compartment here in the liver. And this is what basically what these equations are doing. Okay, we have a gut in the model. This is okay. So this is basically all the blood flow transport equations, and this is the rest. And let's see, like there's definitely stuff broken still, but let's see if we can build the model. Okay, we don't have the creators. Okay, templates. So where did I get the creators from for the oh yeah, I imported this just here. So we definitely have to fix the creators. But we have to add everybody who contributed to the model. For now, I'm just using yes. Let's see. Oh yeah, okay. Here the of course annotations are not working yet. I will just add an empty annotation for now. We have to fill this out later on. Fix me. Okay. It's also good, like always, like if you do you can't do everything at once, so it's important to just always write fix me everywhere where you didn't do things. Yeah, the model base path we don't have, but we should have it somewhere. We have the ramipril model in it. Okay, here we have this. So we have to define the right import for the path. This is coming from XResearch ramipril model. This should be okay. But I just ramipril. Okay. I just saw that. Okay, this looks good. We definitely have like still a lot of errors in here. It's not too many, like let's say it's 12 errors, but I think the most important thing is now, okay, what did we build here? And it's basically what we built here is this part here, like this 3 spider webs we built. And what are these 3 spider webs? It's the 3 substances we put now in the whole body and how they are distributed to the body via the blood flow. And this is basically building this connections we saw in the other image and transporting things like here, like this is basically the arterial compartment, and from the arterial compartment it can go to the liver and so on, and the lung can pump stuff back here. And so this is basically the connection as a species and reaction graph of what we saw in this image. So basically we have 3 spider webs for ramipril, ramiprilat, and ramiprilat metabolites, and these are connected here. Okay. Yeah, so give me a few more minutes and then yeah, if you have to leave, just please leave. I just want to remove fix the remaining errors, and want to fix the remaining errors and see if we can get the model coupling working. So it's more like it's saying it doesn't find certain things. It basically complains that it doesn't find certain ports and things to connect the different submodels. So it can be that we just forgot to put them in the submodels. Let's quickly check. Here it complains, okay, for the kidney submodel it can't find certain ports, and yeah, indeed. We didn't put any ports in the submodel, so we just have to add the missing ports. we didn't put ports for the connection of the submodels in here, and similar for the liver. I just have to similar for the liver. We have to add ports for the things that we want to connect between the different models. So we want definitely to map the volumes on each other, and in the end we want to match the species on each other. So we definitely will need ports for that here. For the basically for the external metabolites in the tissue submodels, we will need ports. For that here. And okay, have to build the model. And similar for the kidneys, for the external species, we have to define, okay, we want ports to connect us to the whole body model. In the liver, in the kidney, we have only these two. And then we can check if the whole body model is building again. Okay, much better. We only have 5 errors. Yeah, here we say, yeah, probably we did messed up here the RAT extern. Could imagine that we did the wrong RAT export could not be found. Okay. And RAT urine port. Okay, the urine. Okay, this I get. So the probably we have to rebuild the model. I'm not sure if I did this, but definitely okay. The urine we also want to map. So this should fix more errors. And then I have to build the kidney model. And I have to build the liver model. Okay, looks all good. And then let's see if we can build a body model. Okay, what is going on? The rat urine. Because we're saying, okay, somewhere we saying, okay, this should somewhere we did a wrong mapping here in the whole body model. I just have to figure out where the urine is. Yeah, here. Basically, no, this looks good. We have rat. The rat can go in the urine, oh? Yeah. So I'm a bit confused right now. What did I do wrong? Okay, let's get the check. It says it can't find the rat ext or the rat urine. So let's quickly check if we really did the yeah, because we screwed up here the kidneys. Because here it says, okay, ramipril can be excreted and ramiprilat. So like we didn't build this right. We wanted to say, okay, only the ramiprilat can go in the kidney. So we excreted basically in the kidney the wrong thing. Okay, not too bad. This can be quickly fixed. So ramiprilat and ramiprilat metabolites can go in the urine, and so we just have to fix these things here. The excretion reaction. So this is the rat excretion, and it can take the rat and it exports the rat in the urine. And let's quickly check that. Okay, rat urine looks good. Let's see that the kidney is built correctly. Okay, looks good. And then we check that the whole body model is built. Okay, perfect. This is already really good. The whole body model is building. And now the only thing remaining is the connection between the tissues and the whole body. So basically we have these tissue models, but these tissue models are not connecting the substances yet. So basically this is just the blood circulation. And then in addition, we have this tissue models, but they are they are officially connected, but they are not, the connections are not resolved yet. So this is the only thing which we have to do. Still, it's resolving the connections, and then the whole body model, or first model version of the whole body model should be there. For that, I'm just adding a bit of a helper function here, which allows me to create all this model at once. So this is just a helper, which is importing the all the stuff. So XResearch, ramipril. We call this models. Why not models? Sometimes it's vector. Okay, we don't have a model intestine, and we call this model kidney, and we call this kidney model. So okay, I will just rename this to be consistent with other stuff. Model kidney, and then our liver model is just called model liver. Perfect. And then we have to make sure that our models have the right names. So we call this just model kidney. And the same for the model liver, we just call this model liver. And then go back to the factory. Okay, this looks really good. We can import all that. And then we want here, basically, we just say, okay, for all these models, we want to create them. So please, for all this model, create the model. So create the kidney, create the liver, create the whole body model. And then we just say now, resolve this connections between the tissue and the whole body. And this is basically called a process which is called flattening. It's basically resolving interfaces and flattens all these hierarchical models in a single model. This is why it's called flattening. But this is more like, okay, it's resolving the connections between the different tissue models and connects everything. Okay, and just have to rename the function. This makes it, this should be create ramipril models. Here. And then we check if this is working, and this is basically now creating first. Yeah, this is basically unreadable. Okay, so probably our results files are wrong, so we have to check. Okay, here's the. So some of our paths are not correct. Yeah, here somehow this is called model, but it should be called models. This is where we updated this, but we didn't update the. We updated the folder, but didn't update the specification here of the folder. And so now it, yeah, basically, yeah, you saw it now created all these different models. If you scroll up, it first created the kidney, then it created the liver, then it created this this whole body. And then it validated that this is correct, and then it flattened it. In the end, we have like this a lot of files, and our final connected model from this different tissue models is this flat model. Okay, and just showing what now happened. It's basically what we see now. Our spider webs are connected, and this basically the connection is done via the liver, because we had these reactions in, and so the spider web of like circulating ramipril can be taken up by the liver, can be in the liver converted to ramiprilat. The ramiprilat can be exported by the liver. And then, of course, this goes back in the circulation, and now ramiprilat can circulate. In addition, we have a kidney here, and so ramiprilat can be exported from the circulation, or alternatively, in the kidney, the ramiprilat could be converted to the ramiprilat metabolites. Currently, we set this to 0, so nothing is going in this pathway, but we already have the equations for that. So it goes to ramiprilat, and ramiprilat can also circulate and then be excreted to the urine. Okay, so this is pretty good. This is a first version of the model. We don't have an intestine yet to absorb all doses. And of course, we haven't run any simulations with the models. So this would be what we do next time. Basically, fix the intestine and run first simulations and compare simulations against some of the curated data. Okay, I will just commit these changes, and I would say then we're done for today. So I did it a bit longer, but it makes sense to just finish this part, and then yeah, we can make it next time a bit shorter. So if you have questions, please let me know. Like I said, please don't feel totally confused. This is just, it should give a general overview what is done. Like this tissue models is pretty understandable. Of course, in the whole body, there are much more moving parts and things coming together. Feel free to look at this model body equation and equations and definitions and try to understand a bit. Also visualize the model in Cytoscape to get a feeling what is in there. But you don't have to understand what's going on all here. And the important thing is we have now blood circulation, and these tissue models are connecting. And now we can start running actual simulations with this model. Okay, so far so good. If there are questions, please let me know. Otherwise, with the data curation, please, if you're stuck or if you're unclear, just ask. Like for instance, like with things like this figures, and it's just like, hey, I have no clue, what should I do with this data point? It's on. I just ask. This makes a lot of sense. Often we can say, okay, ooh, man, yeah, you're right. We didn't see that, and perhaps you should do it differently, and so on. So just let us know what's going on there. Okay, so far so good. Yeah, if there are questions, please ask. Otherwise, continue with the data curation. Yeah, and I see you all next week.
Okay, thanks. Bye.
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 Bye.